In order to define surface integrals of vector fields over a specific surface, we've got to rule out the idea of non-orientable surfaces. Now, an orientable surface, these surfaces have two sides to them. And that may seem like an duh, but in reality, we need to rule out stuff like this Mobius strip. This Mobius strip actually has one side. Whoops. Spell has correctly. There we go. It has one side. See, if you start like right here and you follow along, see now you're on the back side of this right here. You're on the back side. You're on the back side. You keep coming up along here on this back side, and you're on the back side. So now I'm on the other side of this dot. I'm actually on this back side. Then coming back up. Now I'm on this front side, and I'm right here back up to this front side. So you can go round and round and round, and apparently changing sides to this thing. So it really only has one side to it. So the idea of like finding a normal vector or something, what would that mean? Because at one point I'd be pointing what we think is up on the surface and another point down on the surface, like we went around the corner and we're on the other side now, but we never really left the side that we started on. So for what we do, we will consider only orientable surfaces. With an orientable surface, the idea of the top side and the bottom side of the surface holds. Here, the idea of the top side and the bottom side of this surface doesn't hold. I don't know what the top side and bottom side actually is. Now, every point on a parameterized orientable surface has two normal vectors. So if I pick a point like right here, I have a vector that's going to be normal in this direction. I'm going to call this N1. And then going through the surface and coming out this back side here, I would have yet another normal vector. I'm going to call this N2, where N2 is equal to the negative of N1. The choice, whoops, of N1 or N2 will orientate, I should probably say, will orientate the surface. Now, surface orientation is absolutely critical for calculating surface integrals of vector fields, because perhaps the most common interpretation is that what I kind of made reference to a little bit earlier, that of flux. And now, if the vector field is a velocity field for like a fluid in motion, flux measures the net flow rate of the fluid across. We say across, but we're talking actually going through this surface in the direction of the specified normal vector. So if this surface, think of it as a maybe some type of membrane that has no mass to it, and I have a vector field that is flowing in this direction, or possibly slightly in another direction, but it's passing through this surface. So I can use the idea of flux, the idea of a surface integral, to measure how much of this stuff, for lack of a better term right now, is actually going through this surface. And we need to think of the surface as being some type of membrane that has no mass. It's not going to impede the flow. It's more like an invisible boundary of some type. Now, for this to have any type of meaning, the surface must have two identifiable sides. So in other words, it has to be orientable. If we can't orientate this thing, then we simply can't do any of this. It doesn't make any sense. The orientation actually allows us to distinguish one side from the other. So for a surface z equals g of xy, this would define some surface. the unit normal vector is n equals the partial or the negative partial of g with respect to x I minus the partial of g, which is z, with respect to yj plus k over the magnitude of, well, the same thing here. So it's a magnitude of this, so it's going to be the partial of g with respect to x squared plus the partial of g with respect to y squared plus 1. Now notice here that since the coefficient on k is positive, this gives, let's say, upward, an upward orientation. Now, just as a real quick reminder, if we parameterize r as x, y, and z, but z of g is g of x, y, then the partial of r with respect to x cross the partial of r with respect to y gives us a vector that's orthogonal to the tangent plane. Actually, to the tangent plane that containing those two partials. So if you work this out, if you simply take the partial with respect to x and with respect to y, and then do the cross product, this is what you're going to end up getting. And then, of course, to make it a unit normal vector, is simply divide by the magnitude. So, to expand on this just a little bit, I want to say if S is a smooth orientable surface, given in parametric form, by say a vector function r of uv, then the orientation of the unit normal vector is given by n equals partial of u cross partial of v over the magnitude of the partial of u cross the partial with respect to v, based on the right-hand rule. So u cross v, thinking in terms of u and v, the right-hand rule will let your fingers go this way, your thumb's pointing up. That's going to give me the direction of this unit normal vector. That is, well, actually, if we decided that we needed to go the other way, because whatever we're working with, we needed a direction opposite of that, we can simply take the negative of u cross v. I'm saying u cross v, but hopefully you understand I'm talking about the partials of r with respect to u, the partial of r with respect to v, divided by the magnitude of that thing, which is actually equal to the partial of v cross the partial of u over that same magnitude. So this just represents the magnitude. Just a little quick shorthand notation there. Now, in a situation where we're dealing with a closed surface, such as a sphere, then the orientation is either outwards in the same direction as a position vector to the surface, or it's opposite in direction. So if I have a sphere, let's see, how can I do this? Yeah, that kind of makes it look like a sphere in a way. All right, in the center back here somewhere, I'll have a position vector that would go to anywhere on the surface. So think of this as the center of the sphere. And then the normal vector going outward would look like this. And of course, given that same position, the negative of it, the normal vector, would simply be opposite in direction. Now, as a matter of convention, what we do is, for the normal vector going outward, we think of this as the positive orientation. And for the normal vector going inward, we think of this as being the negative orientation. And that really is simply a matter of convention.